Ladies and gentlemen, welcome to the audio slide presentation on the reduction of the air traffic's contribution to climate change, a REACT4C case study. I am Volker Grieve, and for the next 5 minutes I will be discussing the results of our paper, where we combine climate cost functions with an analysis of the transatlantic air traffic to obtain a cost-benefit analysis for one specific day. Climate cost functions are a measure for the climate impact of an individual aviation emission depending on emission location, emission altitude and local emission time. Hence, the climate cost functions are depending on the weather situation. The sketch illustrates the meaning of the climate cost functions, which have units in Kelvin per kilogram of emission. Imagine two alternative aircraft trajectories as indicated by the red and green arrow. The northern aircraft trajectory in red passes through areas with large numbers and hence has a large climate impact in total, whereas the southern aircraft trajectory, shown in green, only collects small numbers and hence has a small total climate impact. The weather situation of this case study is characterized by a very zonally jet stream between the US and Europe, with large wind speeds over the eastern Atlantic. We are taking into account a real air traffic situation with roughly 800 flights between Europe and the US. The costs in Europe are including fuel costs and crew costs, and the climate impact is measured with different climate metrics. We present our results relative to the economic best solution, which is the minimum cost for the whole air traffic flow of our 800 aircraft. This air traffic flow is indicated as the point in the lower right in the diagram. The diagram shows to the left the relative reduction in climate change of the whole air traffic flow, and to the top the related relative increase in costs. We first show the results of westbound flights in red. They have a large climate impact reduction potential of roughly 25% and a low increase in costs of around 0.5%. The optimal climate impact reduction of around 60% requires a much larger cost increase of around 10 to 15%. For this specific weather situation, the eastbound traffic has a lower climate impact reduction potential because the air traffic is more bound to the jet stream, taking advantage of the tailwinds. Leaving the jet stream leads to large fuel and NOx penalties. The air traffic flow is changing along the Pareto front. We are now analyzing these changes in the air traffic flow when we move from the cost minimum situation to the climate optimal situation as indicated by the stars and the arrow in the upper right figure. The large figure shows the flight level distribution of the whole air traffic flow. In the minimum cost situation, which is shown here, the flight level 380 is most frequently used. When we move along the Pareto front, as indicated in the upper right, to the point where we achieve 25% of the maximum climate impact reduction, we only see little changes in the flight level distribution as indicated by the red line. Achieving 50% of the maximum climate impact reduction leads to more flights at lower altitudes, at flight level 300 and 320 as indicated by the blue line. Achieving 75% of the maximum climate impact reduction leads to a situation where most aircraft fly at lower levels 300 and 320 as shown with the green line. And finally, the maximum climate impact reduction shows an air traffic flow which is concentrated at flight level 300 as shown with the green shaded area. To summarize, the REACT4C one-day case study shows that air traffic climate impacts can be significantly reduced by rerouting, and it shows that small changes to the air traffic already lead to considerable climate impact reduction potentials. It further shows that climate objectives, long-term versus short-term, affect the resource and that choices have to be made. Note that uncertainties exist which were taken carefully into consideration. The REACT4C one-day case study is a first step towards an integration of scientific atmospheric prediction tools with flight planning tools for a reduction of the air traffic's contribution to climate change.